We have a special seminar today. Patrick Ewing, who is a postdoc at Michigan State, who's decided to pick up residence in Bozeman. Was a recent graduate of the University of Minnesota, where he did his PhD. His advisor, Nick Jordan, some of you know. He's a good friend of mine. Patrick has been working on a number of systems, and I think he's got some really interesting ideas. It's not in the specs, but I'm hoping to hear more about his research here. He also has a BA degree from Macalester College, and so where are you from, Minnesota?
I'm from West Virginia.
Okay. Go Scots. Good.
All right.
All right, cool.
Yeah, so my name is Patrick. Today I'm going to talk about this pretty big topic of the opportunities that digital agriculture provides for enabling complex, ecologically informed management and commodity grade systems. Something that I've been thinking about a lot for the past maybe 10 years almost. Briefly, again, I just finished my PhD in applied plant sciences at the University of Minnesota, Twin Cities. While there, and independently of that, I worked at scales from the microbial to the regional, and the common thread among all of these is using ecological theory and data science to find opportunities to make our ag systems, which are already super productive, even more productive. So that we're all on the same page about this, digital agriculture I'm going to define as the use of automated and computational tools to collect, process, and operationalize data to manage agricultural systems. So again, I've been thinking about this a lot for quite a while, and so I was really quite heartened to see that the USDA's National Institute of Food and Agriculture, which is their main funding body, put together a data science summit in 2017. And there, one of the questions they asked their panelists was, what are the most promising opportunities for data-driven advances in agricultural and food production systems? And they came up with this very wonderful consensus response of a more productive, sustainable, economically viable agricultural system that is resilient in the face of increased climate variability. And these data science tools will provide improved predictive capabilities to inform management decisions in the field. Right? That's a lot of multi-syllabic words. What does this all mean? What is really a more productive and sustainable and economically viable agricultural system? So I'm going to give you an example, and this is a real example. A few years ago, Walmart decided that they sell a lot of eggs, right? And they wanted to sell eggs that were cheaper, and they thought it would be also a good business practice to have a lower carbon impact on their eggs. So they decided that they wanted to reach down through the supply chain and go to the source of that carbon, which was, turns out, the nitrogen fertilizer used to grow the feed for the chickens. In this example, we see a few different types of goods that agricultural systems produce, right? We see some economic things, cheap eggs. We see carbon emissions. I would argue that there are some cultural issues embedded in that example as well. We want agriculture to produce all of these things. We want it to be multifunctional. If we want agriculture to produce a variety of different things, though, we need to treat different locations in different times differently. We need to manage agriculture complexly. I'll support that with this example, a simple example of looking at the trade-off between yield and water quality when we're growing corn. So this is a modeling study that I did a couple years ago. The premise or the idea is that we want to grow a lot of corn here in Iowa and Minnesota. In this map, the yellow is corn, the green is soybeans. You can see there's not a whole lot else there, right? We want to grow a lot of corn. To do that, we have to add nitrogen. That nitrogen tends to leave and decrease water quality both like locally, contaminate drinking water, and down in the Gulf of Mexico causing that dead zone. So we have this trade-off here. We were interested in looking at that trade-off and seeing if there are opportunities to get more of both goods. So these graphs on the left, on the y-axis, we have modeled water quality, and on the x-axis, as we go out, we have greater yield. And as you move down along either this purple, or this green line, you are adding nitrogen, so increasing yield, decreasing water quality. This purple line assumes you're treating every acre in each county the same. The green line assumes that you're allocating a given amount of fertilizer differently in different areas depending on how much of an impact that area has on yield or water quality. So you can see a couple of things from this graph. First, there are some areas like Pocahontas County in blue where if we treat every acre the same, we're going to produce a lot. And we'll also, and not too much of a trade-off in terms of water, in terms of groundwater pollution from nitrates. Other areas, you see that this green line is quite a bit further away from the purple line, like 1 count up in that green square at the top of the screen. So when we look at the landscape that we get, so that space between that purple line and that green line is the extra value, if we go straight up, the extra water quality we could get without decreasing overall county yield just by rearranging where we put that nitrogen. And so to illustrate this, I want to draw your attention to this graph marked B in the bottom left. Juan County, again, is up at the top and has this dark green spot signifying that if we value yield and water quality about the same, we don't want very much fertilizer in that area, but we do want a lot. But we do want to add fertilizer over the rest of the county. The point being that if we manage nitrogen in a complex way across space, we can get more of both goods that we want. So complex management can mitigate these trade-offs among these different valuable goods that we want for a multifunctional system. Complex management comes with some challenges though as well, notably labor and knowledge intensity. To demonstrate this, I'll use this experiment put out by Adam Davis and Matt Liebman and some other people in Iowa and Illinois. They looked at a variety of goods, ecosystem services that agriculture produces. The way to interpret these graphs, this graph, the axes at the top, things like soybean yield, we want more of. The ones down at the bottom, say herbicide use, freshwater toxicity, we want less of. And so we can see that, and then there are 3 different cropping systems of increasing complexity. Corn and soybean being the simplest, corn and soybean followed by a small grain like wheat, and then alfalfa being the most complex. We can see, and they found that these simple cropping systems produced, they were pretty darn productive, right? But they also had these costs, which we know of, whereas these more complex cropping systems were also productive, but didn't have these negative impacts that we want to avoid. But again, we still see the landscape looks like this, right? Very simple. A lot of that 2-year rotation there. Because these complex cropping systems require more labor, and if you're going to grow 4 crops, you need to know how to grow 4 crops. That's a lot more knowledge than growing 2 crops. So we know more complex ag systems can produce more goods, but it requires more labor and knowledge. This is where the digital agriculture comes in. Right? Digital agriculture is a way to supplement knowledge and labor. And so computational agroecology, which is a term I just think is great, and totally oxymoron, is one way to think about how to make these systems that manage complex systems by supplementing human knowledge and labor. There are a few components of these systems. We need to acquire data. We need to use that data to create some knowledge through some decision support models, or we're moving towards more complex things and artificial intelligence-based things. And then we also want to support labor through automation by robotics and other sorts of autonomous types of systems. So this is one potential way to achieve and create these complex multifunctional systems in our current commodity grades, to apply this, right? So today I'm going to talk about two examples from my work that I see as real opportunities for complex and ecologically informed management. These opportunities are adaptively managing the soil microplant system, and then guiding targeted diversification of current Midwest cropping systems. And the outline in both of these sections in general will be able to give you some context, first of all, and then talk about some of the results that we have, and then look towards the future. What might we be able to achieve, and what are some potential systems to achieve that? So this first system, or this first opportunity that I see, adaptively managing the soil microplant system, comes directly as an extension of my dissertation work, which was embedded in this big multi-state, multi-institutional, interdisciplinary research project, which we call the Precision Zonal Management Group. These are where all the field sites are. So it's a really wonderful, rich data set and engaging group of people to work with. By precision zonal management, we don't really mean precision agriculture in the sense that most people understand it. We mean the ability to create distinctive soil functional zones at the row-interrow scale. So we're working with row crops, corn, soybeans. They're generally planted 30 inches apart. So to describe what this means, I'll give you first a uniform system, the well-known chisel plow system. No-till would also be a uniform system where we're treating every acre in the field the same. And in contrast to that, our model zonal system was this pretty weird system called ridge-till, which features permanent washboard topography where the ridge top is where we plant, and then the interrow tends to, because of this topography, gather residue and moisture. And still a highly disturbed system, but the disturbance is very targeted, as marked by these red boxes here. So this is the system that I was working in. I was really interested in microbes. Right. First of all, this is what these systems look like in the field. Right. So on the left, you have that ridge-till zonal system. You can see the different zones there. On the right, the uniform chisel plow system. I was, and I still am, very interested in microbes, managing microbes, because they're in many ways the factories of multifunctional ag systems. They do all sorts of things that we're excited about. They can control plant disease, cause plant disease, increase stress tolerance, build organic matter, cycle nutrients. All these things are essential for productive and multifunctional ag systems. It would be so wonderful if we could manage them predictably and in a way and effectively. So working in this system challenged me to think about this pretty hard. I would say that we've been managing microbes as long as we've been doing agriculture, but it's been in a sort of naive way. For example, we've been growing legumes for millennia, right? Legumes, of course, use rhizobia to fix nitrogen, which increases crop yields later on, we've noticed in general. But we didn't discover rhizobia even until 1888 or so. So we've been doing this for a long time, but we haven't really known that we're managing microbes. More recently, as we've gained more knowledge, we've become a little bit more deliberate about things. And looked at managing microbes in a way that fits into the traditional agricultural research approach of the randomized block, where we have our treatments, say till and no-till, adding a microbial inoculum or not, and looking at the output that we get from that. The problem with this approach is that it's really hard to transfer it to new contexts. It's pretty hard to reproduce. The approach that I've developed is this spatio-temporal approach, looking at, instead of the management per se, looking at the soil habitat as the driver of the system. We know that microbes, the services that microbes produce respond to both what the microbial communities look like, how they're behaving, as well as the habitat that those microbes are experiencing. What do I do about this? Oh, right, of course. Okay. So, where was I? Right, so this fits really well into this digital ag paradigm, actually, because we have a really, really excellent ability now, and it's getting better and better, to manage this, to measure the soil habitat across space and across time pretty accurately and pretty densely. We also have really high ability to measure some of these microbial services, and especially plant responses to these services. Again, at dense scales, spatially and temporally. To demonstrate the potential of thinking about managing microbes this way, here's some quick results from my dissertation, which I looked at ways to increase maize phosphorus uptake by arbuscular mycorrhizal fungi. These mycorrhizal fungi, or mycorrhizae, are they're fungi, so they're microbes. They're symbiotic with plants. They're best known for trading phosphorus that they acquire from the soil to the plant in exchange for sugar. So they're feeding the plant phosphorus is feeding them energy, and they're helping each other out. We want this relationship to be a good, strong relationship. So looking at a simplified version of that Habitat-Affect-Microbes, looking at the core part of it, these microbial services we might measure as a proxy by greater maize phosphorus uptake, and we might expect higher uptake to be a result of higher mycorrhizal activity, and we might induce that by creating the right soil habitat, moist habitat with low disturbance. So I looked at this, the data I'll present is from about 2 weeks after planting, so the corn's about the size of your palm, and this is really the time, getting into the time of peak susceptibility to phosphorus deficiency for corn plants. Their root systems are really small and shallow, and they've just depleted their seed reserves. And so I'll again also be looking in the row environment of these ridge till and chisel plow systems, because that's where the roots are. So what do we observe? Well, in terms of this response, maize phosphorus uptake, in the chisel plow systems, we see phosphorus uptake levels that translate to being just about sufficiency. So these plants can grow as fast as they can without being phosphorus limited. In the ridge till system, we saw 40% higher phosphorus uptake, which means that these plants can grow 40% larger without needing to get more phosphorus from the soil. That's quite a bit of buffering capacity. Or you can interpret it as you don't need to add as much phosphorus to your system. What was driving this? Well, we saw a few soil habitat parameters that were driving the system. First of all, the ridge till system in the row at this time is not disturbed, and that was increasing the abundance of these mycorrhizal fungi. The other effects, higher bulk density and higher moisture, didn't necessarily respond to ridge-till per se, but they still increased phosphorus accessibility to both the fungi and the plants. And so these two pathways ended up being about equally important to each other. So why am I talking about this in a digital ag seminar? I'm talking about this to demonstrate how powerful thinking about managing microbes from this habitat perspective is. So this Habitat-Affect-Microbes approach integrates really well into these new flexible systems modeling paradigms. I use Bayesian leaf networks to analyze those last results that you saw. And they also give actionable mechanistic results. I didn't necessarily say, you should practice ridge-till. Instead, these results say, if you reduce physical disturbance, if you increase bulk density, if you increase moisture, you should have more phosphorus in your plant. We can imagine a bunch of different ways to do that, which means that these results are management agnostic, and any management system that creates the right soil habitat in the right place at the right time should, hopefully affect microbial services similarly. Which suggests, therefore, that we can manage microbes precisely in space and time if we have the right tools and the right monitoring capabilities. So I would like to extend this model then and think about how we might manage nitrogen mineralization spatially, explicitly, and adaptively. So to give you some quick context about nitrogen in these cropping systems, I've talked about it already a bit. Nitrogen is the second most expensive input in corn systems. It's essential for high yields in most parts, and it's a major source of pollution. Corn acquires most of its nitrogen in mineral form, which is ammonium and nitrate. Most of this corn, N, is organic matter. Fertilizer actually only provides less than half of what corn picks up. Moreover, of all that fertilizer that we're applying, only about half of it actually makes it into the corn plant in a given year. The rest is either lost or cycled through organic matter. So the cycling and this mineralization are both microbial processes, and we would really like to manage that to ensure sufficient nitrogen availability for high yields and with maximum nitrogen retention in the soil. I'm going to show you a nitrogen mineralization model now from about 30 years ago. This model, I like it for a few reasons. It shows some of these parameters that we might want to measure as we're predicting nitrogen mineralization in terms of soil environment, in terms of crop growth. It highlights how these central microbial processes, mineralization, nitrification, are central in the system. And also because it's the back end of at least one of these current contemporary adaptive nitrogen management tools. These tools are modeling nitrogen mineralization and crop uptake across fields in response to weather, so that farmers can then apply fertilizer nitrogen when and where they want. I'm proposing repurposing this. Instead of using it to apply fertilizer nitrogen, instead tweak this mineralization area to induce more mineralization. This is what a system to do that might look like. We might prime the soil at the beginning to build organic matter. And in the past 10 or so years, we've learned a lot about how to do that, what habitat microbes need in general to support building organic matter. And then throughout the season, monitor it using some of these modeling tools that I've mentioned. We also have really excellent data collection tools now of both crop nitrogen status, crop growth, and some of these soil parameters. And so if we predict that we don't need more nitrogen, then we just keep on going building organic matter. But if we do decide that we need more nitrogen around, then we try to induce mineralization. And again, we have a pretty good idea of what kind of soil and habitat microbes need to mineralize. So this is a great example, I think, of ecologically informed management that is totally requires these tools of digital agriculture. And the trick, and so the limitation here is that we haven't put these systems together yet. So moving on to the second opportunity that I'll talk about is guiding targeted diversification of current Midwest cropping systems. So to give you a bit of context about agriculture in the Midwest, which is very different from agriculture here, but I'm guessing that a few of you know a bit about it. We grow a lot of corn and soybeans. Up to 95% of the land or more in some areas is corn and soybeans. And in those areas, if it's not one of those two crops, it's probably a row ditch. Moreover, between 25 and 50% of land in these states is deemed suitable for drainage. We have more water around than we know what to do with it. And so we get rid of it, and when we get rid of it, it tends to bring nutrients along with it. This water and these nutrients are resources that we could use. Finally, our growing seasons are now over a week longer than they were before 1960. This again is more heat and light that we could use to turn into productive crops. So there's a consortium across the Midwest called the Forever Green Initiative that has recognized this and is working to develop crops, cash crops that grow in these quote-unquote shoulder seasons, early spring, late fall, to take advantage of these unused resources. The idea, and so the Forever Green comes from the idea that the landscape will be always green instead of having these fallow areas. Their two best-known examples are Mycorrhizal, which is a perennial wheatgrass, and then field pennycress, formerly known as a pretty nasty weed, now winter oilseed that creates, seems to be pretty good for jet fuel. And so a third crop coming out of here, and one that I spent a lot of time working on, is winter malting barley, which should be a little more familiar to you all here too. So winter malting barley has a few advantages over these other two crops. One, there's a craft brew industry in Minnesota, much like there is one here, and they would love to use Minnesota malt. So it has a market. It also has really excellent environmental benefits, similar to a rye cover crop. It's a great nitrogen scavenger. It holds the soil in place. And, there are varieties that are pretty productive and well developed. So we wanted to grow winter malting barley in Minnesota. We used a site in Lamberton, which is in the southwest part of the state. Winter malting barley has some challenges, though. One of the biggest ones being that it really doesn't survive that consistently. So we wanted to try to manage this risk, and by focusing on the spring regrowth time. So in the spring, when the barley regrows, if it doesn't grow at all, it's pretty obvious what to do. You plant something else. If it's all growing and the field looks good, that's great. You keep going, you harvest it. The tricky part is in these middling times when some parts of the field look pretty good, some parts maybe so-so, and so this becomes a risk management point, the point to manage risk for crops. Excuse me. Anyways, so we approach this by using some aerial imagery. This is collected from just a DJI drone. Using that imagery to estimate plant populations. From that estimated population, predict the yield whether or not that would be a profitable use of that land, and depending on whether or not it was, either harvest the barley or manage the corn, or plant some other crops such as corn. The same logic can be applied to a bunch of similar risk management situations. In Minnesota, we have quite a lot of drown out in some areas from wet springs. We have hail. If we're planting very early, we can have some damage from late frosts. And I'm sure that there are similar issues here, including also this overwintering issue. So these are tools. This is an application, pretty low-hanging fruit, that uses these digital agriculture tools to manage risk now and improve management now. What I want to talk about now, though, is how we can use these tools to design cropping systems of the future. So in addition to just try to grow winter malting barley, we wanted to grow winter malting barley in a double crop with soybeans, which has a few advantages. It increases farm income and returns to land and capital because you're using the entire growing season. You're capturing more resources. And then if you do this thing called relay cropping pictured here, where you plant the second crop into the standing first crop, you can potentially have higher yields as well. This picture also really highlights the challenges of doing this. Challenge number one, these soybean plants are growing in partial shade, and they are not bred to grow well in partial shade. These barley plants are starting to lodge. They're not meant to grow with these spaces between the rows. They're meant to be planted pretty closely together. 3, you can see there's a gap in the row over here. That's where our planter ran over the barley as we were planting the soybeans. Our machinery isn't made to plant into standing crops, to plant complex mixtures. When we tried to harvest this, we had some losses from lodging, of course, but we also had a really hard time holding our 30-foot combine head up over the soybeans to avoid damaging it too much. Our machinery is just not there, right? And then finally, even though we have all these brewers around in Minnesota that want to brew Minnesota malt, we need maltsters that can handle the small volumes that we're producing at this point. We need to reach a critical mass in order to make it an economically viable thing. So this is a very multifaceted challenge. I've done a lot of thinking about this, about how to overcome these challenges in Minnesota. We put out this paper that describes this innovation platform, which is the model behind a lot of the Forever Green work, where we have such working groups as germplasm development, cropping systems integration, agronomy, and then working on this end use and supply chain stuff. The idea being that all these people, all these groups need to be working together to share their needs and then to figure out how they can address each other's challenges. Digital agriculture comes into here, and I'll focus especially on these two areas, the agronomy and the breeding side. As an agroecologist, digital ag has enormous potential to help these out. So I'm going to propose this system, a two-part system for breeding and developing the agronomy of these multi-species cropping systems of the future. On the left, we have a design phase with the goals of predicting crop idiotypes or what sorts of traits and growth forms crops would need to grow well in mixtures, as well as figuring out when, where, how densely to plant them with each other, these agronomic configurations, with the goal of maximizing light water nutrient capture. That side can form and be informed by the enacting side, where we use these rapid breeding tools and our ever-increasing knowledge of plant genetics to develop some candidate varieties, as well as design the machinery that can actually manage these weird agronomic configurations. Ideally do that in an on-farm setting to look at some of the challenges that arise when scaling and the agronomic side of things, as well as produce enough to start integrating these crops into markets. One tool that will help a whole lot on the design side that's available right now is this FarmBot from California, which I view as a rapid prototyping tool. So what this is a gantry system, and you can see here a bunch of different leafy greens in this situation that are spaced kind of randomly. What it allows you to do is it allows you to plant a variety of different plants, species, or varieties in any sort of configuration and density that you want. So this is a rapid cropping system prototyping tool to gather data to feed the modeling side of things. And then when we go out to the field, such tools as University of Illinois' Earth Sense robot would be really, really valuable for collecting plant phenotype data at high density and high resolution. And so combining these two types of systems will support this broader goal of rapidly developing cropping systems that capture more resources and produce more economic, environmental, and social goods. So these are the two examples that I've talked about today. Managing the soil microplant system, guiding targeted diversification of current Midwest cropping systems. Digital agriculture is essential and will allow these two types of ecologically informed management systems to develop, especially if we can, especially following this framework of computational agroecology with the goal of supplementing knowledge and labor, right? And so I want to remind us all that the goal, of course, is to create this more productive, sustainable, and economically viable agricultural system. So with that, I would like to thank my collaborators and colleagues at the University of Minnesota, especially, that have given me a lot of help here, as well as here, the Institute on Ecosystems for putting, and Bruce and Madison for organizing this seminar, and then Steve at KGBM for recording. My funding came from the National Science Foundation and the USDA. And these are the institutions that have hosted or are currently supporting it. So thanks a lot. So now I'll take some questions if you have any about this talk. And I'm also pretty excited to think about applying some of these systems, computational agroecology systems, to Montana's situation. What opportunities do we have here? Great, yeah. Steve.
Yeah, so I'm wondering about what the state of machinery is for being able to, for example, fertilize a large field with different mixes of different components, maybe in different regions of the field, and then be able to correlate that with different yields across that field. Does that even exist in experimental farms, or how far along is that?
I don't know about different mixes of fertilizer necessarily.
I can see if you wanted nitrogen
Right.
and some other component, and you'd do some
Right.
different combinations.
So these adaptive nitrogen management tools work really well with this variable rate fertilizer technology, which is pretty well established, though not necessarily horribly widely used right now. The idea being that, and so these are a form of automation that change the rate of fertilizer that you put down based on what you think you need based on soil type, for example. And so people are starting to integrate that with measuring crop growth through like drone imagery, for example. and found, I think, some pretty good results from that. So it's starting. It's definitely starting, and in some areas it's well established.
I was going to ask a question, and he just sort of answered it. How do you see remote sensing as playing a larger part of this digital agricultural age? You did show the one example of the drone image, but can you speak to a larger role for remote sensing?
Yeah, remote sensing to me fills many of the same roles that these drone imagery things do, and aerial imagery does, especially as resolution increases and sensing and sensitivity increases. And so right now, I know people are using it to estimate biomass production. You can use it to look at moisture in their fields at least. So right now it's being used to measure a lot of these environmental and crop response variables. I believe that there are some pipelines to integrate that into management outcomes as well. Yeah, it's definitely going to be an important tool. And it is an important tool already.
So I'm curious about the scale at which data gets integrated into your computational components, and then how the application, the inference space for that. And so you're across a lot of these scales. Most of the time I'm interested then in who are you trying to inform? Is this to inform policy? Because it seems like you scale up to that kind of level of saying we need a more diversified kind of system, or the discoveries would be relatable to that scale.
Right.
More so even than maybe a decision that's made on a farm, on the field.
Mm-hmm.
Is that an accurate, draw those connections on the scale versus the data, the computational piece, and then the outcome part.
Mm-hmm.
What are the scales that are meaningful?
Mm-hmm. So there's this trend towards monitoring and validating on-farm practices, I think, is a good way to think about bridging these scales. So I gave this example of Walmart being interested in managing their supply chain a little more closely. You could imagine policymakers doing the same thing to, say, manage nitrogen inputs, or with a goal of reducing water pollution. This is totally a landscape scale thing, but the decisions are happening on farm for the most part. And a lot of the processes that are driving these decisions, especially these microbial processes, are happening at even smaller scales than that. So integrating models that are built for different scales is definitely a challenge. Right? And I wouldn't necessarily say that these adaptive nitrogen management models, which are great for the field scale, measuring these microbial processes in aggregate at the field scale, are necessarily that appropriate for meeting environmental quality goals at the regional scale. But that's something that we can certainly investigate. Does this answer your question?
No, it helps. I mean, I saw those different scales that you you could implement these things. I guess, and you identify the struggle of sort of implementing it into the current systems.
Definitely.
And the challenge to me, though, is how exactly you use this. There's this whole spectrum of tools out there in the computational realm. So utilize those in some way that suits the agriculture, finds the most suitable agriculture. Is the real challenge. That's, it was curious to see how you integrated these different things.
Yeah.
And I'm very curious to hear about things like pirates.
Yeah.
That's never heard. So that was having insight into those processes through some sort of surrogate assessments is a huge, very fruitful area, it seems like to me. And it's being explored primarily in the southern. So, other questions? All right. Well, thank you again.
Yeah. Thank you.